English to represent given or known information. Okay, our first question is what are so-called all known information and how should I represent them? So can I just say that this? Okay, so I'll give you like 1 to 2 minutes to think about how should I represent it to say that given or known information. Write it down the so-called condition.
Are we missing the input for day 2? Does that
No,
matter?
day 2 will only affect, day 2, the input of day 2 will affect only day 3. Okay, we only care about this day 2, the state of day 2. We do not really go to day 3 yet,
Oh,
so
okay.
yeah, so we don't really miss the input for day 2. Because day 2 will only go to day 3.
Oh.
Mm-hmm. Okay, anyone wrote it? If I wrote it, I should write it in this way, the so-called the condition we know. Okay, so the condition, first thing we know is the first day is rain. Okay, this is actually the only concrete state we know. Okay, so first day is rain. And then the other state, exact state, we don't know anymore. But we know that the U0 and to U1 is rain and rain. And we also know Z0 and Z1 equals sleep. Let me just use L to represent sleep, it's easier. Sleep and sleep. So these are the conditions for this. And the second, basically, it's the same thing. Yeah, question?
Just to check, where did it say that Z0 is L?
What?
Does it say like Z0 is sleep?
Sleep, yeah. Z1 doesn't really matter. We don't really give you Z1 because Z0, because it doesn't really matter, right? Because we know X0. The observation of day 0 depends on the state of X0. But x0 we basically know it, we have it's raining. Okay, so we don't really know what is z0. Oh, sorry about, you mean this is z1, z2, right?
Yeah, that's right, 'cause I was like, I don't know.
Okay, sorry about it, yeah, good catch.
So I was just confused.
Right. So this is actually what we really wanted to know. It's long, it's complicated, I agree. And now, can we make it simpler? The simple simplification number one is that how about the first day, what's the probability of it just rain?
100%.
No, the first day here is 0 state.
Oh,
First day.
80%.
First day is how shall we represent it? I just say, first day, it's just rain, what's the probability? How should we annotate it?
X1 given X0.
Given x0.
Given.
So x1 equals rain, given x0 equals rain.
You can
How
kind
does you use
I mean, x0 for sure is
Yeah.
green, it's not really a condition, it's just for sure.
Oh.
Okay, so I mean, here, this sentence, if you do not write it, it's kind of fine, because it's not really a condition, I mean, it's actually certainty. It's something certain, so yeah, if you don't write this part, it's fine. So, I mean, the first day it rains, what's the probability? Simply is this.
1.
What,
I mean,
we just
small.
annotate it
Yeah,
like
0.
this.
Okay.
The first day is, what's the probability of first day is raining? And let's think about this question first. What is the probability that the first day is raining? And previously in that Markov chain, we say that it depends on the previous day. I mean, it's the probability of previous day and previous day, right? So on one chain and one chain. And here we can also say, what's the cause of the may cause the rain? The first thing is the previous day, the probability, right? So previous we say that for sure it's raining. So previous day it's raining. It's these two rows. All right, it's 100%. And we may pray. We have two types of pray. We pray for sun. We pray for rain. And no matter what, the next day may rain. Right? So if we write it fully, it should be given and the first day we pray for rain. And sorry, not the given, but and. So and second day is raining, and the first day is raining, and our first pray is for sunny. So it's sun to be, right? So there's no third route you get rain. Right, so you either pray for the second day rain, is either you pray for rain or pray for sun, because the previous day is just raining. Okay, and if you think more, actually for third day it's a little bit more complicated. But the second day is still easy. The only thing is that the first day raining is a certainty. Okay, and then the probability of this thing, if we write it, this becomes equals rain, u0 equals rain. think I typed something wrong. Sorry, actually I typed something wrong. The first day rain, the probability depends on the previous day's probability and what we pray. And do we really need to get this probability here? Yeah.
That's what I was gonna ask, 'cause we know that U0 is rain.
Yeah, so actually what I wrote here is wrong because the U0 equals sum, the probability is 0, so we didn't really need this part. Right, so actually this part I was wrong, I shouldn't write it here. So the second day to be rain, it totally depends on that what we pray. All right, and then what's the probability of these two? We say for sure the first day is raining, and for sure we just prayed for rain, right? So this is 1 and 1. So basically what we need to find is only this part. And how do we find that?
Oh, can we use base theorem here? Can we use base theorem here to calculate that quantity?
What base? You mean this value?
Oh, it is.
What does this mean? It means first rain day is rain, and we pray for rain. What's the next day? The next day, what's the probability of the next day to be rain? So here I should write one more, x1 equals rain. So yeah. Right, so basically it simply means this one, right? The first day is rain, we pray for rain, and the second day it turned out to be rain. The probability is 0.8. And it's actually what this value gives us. Question? All right. If no question, then let's think about the second. So let me just copy it here. Pxy. Oh, sorry. I mean, this part is not really important. And u1 equals rain. And so p u1 equals rain. Okay, and this one certain, so it also equals to 1. And what you take out to find just this. And it's also in course slide actually. Although the course slide actually write something that shouldn't write. And yeah, right, so let me just copy it here. So this is the probability that's the first day to be raining. So P1 is 0.8. So naturally you may ask, what's the probability of first day to be sunny? Yeah, 0.2, right? I'm sorry, I probably need to accelerate a little bit faster. Okay, but let's at least try to get the first day's probability done. All right, and then the second question is that what is the probability that on day 1 we will observe the cat to go out if we know there is 80% probability that it's rain and 20% probability it is sun. So question is probability of Z1 equals sleep.
You have to subtract it, don't you? You have like 0.8% that it's raining, and if it's raining, the cat only has
Right.
0.8% that it's sleeping, so you have to.
So rain
It's 0.8 of
0.8 and sunny 0.2. And then you go this table, right? So you get the probability of sleep and wake. I mean sleep and out, right? So now you do is basically we say that it's a probability that your first day the cat sleep given that the first day is raining times the probability of first day rain and plus the probability of cat sleep given the first day is sunny times the probability of first day is sun. Okay. And then if you sum them together, you basically this thing is 0.8 times x1 to, I mean the first day to be rain is 0.8 and this one should be raining cat sleep, right? So 0.8. And the first day to be, I mean sunny and the cat to sleep. Sunny cat sleep is 0.2. And the probability of the first day sunny is also 0.2. Right, so you add them up, and so this is 0.68. And of course, let me just write this. So first day, the probability of the cat sleep is 0.668. And the first day cat go out, then is 0.32. Right, so let me also write here 0.68, 0.32. And now my question, the third question is that, yeah, we indeed observe that the cat actually sleep in the first day. So now our question becomes, what's the probability of its rain given our cat go out the first day? All right, so now question is, for the first day, our cat, what's the probability that the first day is raining, given that we indeed observed the cat go out. Let's say that by forward propagation, we know that 68% cat may go out, 32% may just stay in home. Sorry, actually I say wrong. So 68% is stay home and 32% go out. But we indeed observe it just stay home and it's sleeping. And the question is that then we want to infer that what's the probability that it's raining?
Sorry, I'm just looking backwards.
You just need to use the Bayes, right? So Z1 sleep given XY rain times PR. I mean X1 equals R. Over P Z1 sleep. Am I right? Okay. And then second day, and we can get into this equation. So basically this thing is 0.8, and the first day is raining, first day raining is 0.8, Z1L given rain is here, right? So this value corresponding to this value, and it's also 0.8, and the ZL is actually from here, so it's 0.68. And it's around 0.941. And of course, then what is the probability that it's sunny given the first day is the first day we see the cat sleep? And then it's also the same thing. So basically, you can either go this route or any alternative route. So I can write down the Bayes, or I can.
So one.
Yeah, there's still just like two, right? So okay, so this is how we get to the first day. And now question, how about the second day? We continue to observe sleep. So basically, it's the same idea, right? So we just need to change xy to be x2, z1 to be z2. So let's just try it quickly, and let's see that whether what we can get. So we say that what we wanted to do basically is the p x2 equals to r, given the second day we observe the cat sleep. And this thing then basically equals to p z2 given, z2 sleep given x2 is rain times x2 equals rain over z2 sleep. And which one we know, which one we do not know.
We know the probability of cat sleeping given that it's raining, right?
This one we looks like we do not know, right?
We don't know that one, we know the one before it, I think, right?
Hmm?
Do we know the condition where the cat's sleeping before it's raining?
Right, so you just go on to calculate these two, and do we know this part?
Yeah.
Yeah, we know that one.
One.
Or do we?
Rain sleep. Zero.
Yeah, so x2 is rain, z2 is sleep, right? So x2 is rain, z2 is sleep, so this one definitely we know it's basically this value again, right? So what we only need to do, what we really need to calculate is this part. Okay, so let's try to quickly calculate it. X2 equals R. Then basically, what route we may have? So
Day two, not rain.
the first day is raining, and we know that we pray for the rain, right? So actually, so basically is the first day, second day, given that the first day is raining, and we pray for the rain, times the probability that first day is raining, times we pray for the rain, plus the second day is raining, given the first day is sunny, and we pray for the raining. So basically, x1 equals sunny, and first day, and we pray for the rain. And this value is exactly from here. So rain, and so raining day, we pray for the rain. The next day is 0.8. And first day it's raining is also 0.8. The first day we pray for the rain. Day one we pray for the rain. What's the probability?
1.
It's 1, right? We said we prayed it. Right, so it's 1. And the next day is rain, given that we pray for, it's sunny, we pray for the rain. Which row we should look at?
Sunny rains
So sun, we pray for the rain, right? So it's this row is 0.7. And the probability of second day is sun, first day is sun is 0.2. And the third one is also just 1. And then the whole thing basically becomes a big number called so basically rain and sunny and then how about Z2? It's just a forward propagation here using this table again, right? So we say that Z2, can you erase this part? Z2, the cat sleeps again, and basically equals to the cat sleep given x2 is rain times probability x2 equals rain, and P2 equals rain given x2 is sunny times px2 equals sunny. Right. And then you propagate forward, and you can see that this part equals to rain sun, rain sleep 0.8, and times the probability that you second day goes to rain is 0.794. Just now we calculated, and the probability of sun sleep, 20.2 times this one, 0.206. So this becomes the second day the probability that our cat sleeps, and it should equals to actually my solution didn't really write it. You can calculate it by yourself, and there is another alternative way, which is we said that if the evidence is not clear, is there any other possibility we do it? We can calculate its reverse and do normalization, right? So x2 equals sunny. Given Z2 is sleep, and so basically Z2 is sleep given x2 is sunny times p x2 equals sunny over p Z2 equals sleep. Okay. And this part, do I need to go further about normalization?
Yeah,
Probably. Okay. All right, so we say that we have these two alternatives, right? And we have these two alternatives, and the first part, the alternative is, this value should be x2 is ring given the, x2 is ring given the second day is ring. What's the value of that? Just now we calculated. It's 0.8, right? It's from the table. So 0.8 times x2 is ring is 0.794. Right, so basically this part. And over PZ2 is sleeping. And this part, x2 is sunny, and given our cat is sleeping, is also from here. So sunny, given cat is sleeping, is 0.2. And times x2 is sleeping, 0.206. And over PZ2 equals L. And they sum up should equal to be 1. Right? So and then you can universally calculate PZ2 equals L, basically just a vector. You do normalization, and you can find, that means this whole part basically equals this, and this whole part basically equals to this. And for solution, this part actually equals to 0.939, and this part equals 0.601. The ratio of these two matches, and they sum up to be 1. I'm sorry, actually copied wrong. 0.61. All right, so here our cat observation is only sleep and sun, so it's kind of easy, but if our status has more, just not more than sleep and sun, and actually the calculation will be, the normalization will make our life way easier, because we just do not need to enumerate all the possibilities to get this evidence anymore. Okay, so now you can continue to think about the day 3, and actually that's a question. And if day 3 we continue, and what's the probability of the day, what's the status of day 3? Okay, anyway, so since the time is up, I will just quickly, go through and why we discuss this stupid price and sleep. Because in robotics, basically it's the same story. Let's think about a robot. You give it a command, please go 3 meters per second. And you have a sensor and say that how far I have traveled. And question is, your sensor, you say 3 meters per second. It's not really accurate. Maybe 2.5, maybe 2.8. And you can model that you give 3 meters per second, what's the probability to go 2.8, 2.9? So basically, this U is your command to the robot. It has a probability that affect the output, right? So that's why we discuss this, and we should have a table regarding to the U and X, previous X, and how they transit to X1. So the command to the robot is a probability. And now you have a sensor. However, the sensor is also not accurate. You know that you can calibrate the sensor, so say that it's 3 meters, at what possibility it's actually reading 2.9, at what possibility it's reading 2.8, right? So it's also a possibility of state transition, so it's just a table like this. And now what you have, or you know, is that previously I give you a command, 3 meters per second. And now I read, so previously I give you command 3 meters per second. And now I have read that you actually travel 2.9. Question that where the robot actually is. Right, so you give command 3 meters per second, you read 2.9, where the actual robot is. So that's actually Markov localization, the essence of Markov localization. Alright, so this table will be replaced by a longer table, but essentially means the same thing. And here, this table will be replaced by the sensor model. This replaced by your motor model, probability motor model and sensor model. And your task is, given those models, infer that where the robot actually is. Alright, so that's the purpose we discuss this rain and sounding. I mean, we are not freelance, there's no need. And I put this problem to be a bonus question for the robot localization. It's just like a crazy enhancement of the previous cat model, because we have only 2 states, and robot that gives 7 states, and sensor reading is another 6 states. And sensor reading is also another 6 states, but I encourage you at least read it and know that what the question means. Doesn't really matter you answer some question or didn't answer at all, but I indeed wanted to just read the question and understand what does the question really mean. Okay, all right, so that's much about today's lecture, and still, I mean, I will begin to grade your solution tomorrow. Okay, but if you really can, you can still send me email, and if you still struggle and you want to continue the struggle, send me an email, I can still give you extension. All right.